Hi, I'm Adam Taylor, and we're going to be doing a rerun of the Design for Mission Critical FPGAs talk that I gave just this week at FPGA Kongress. Now, looking at the main page, you'll notice that I say systems in brackets. The reason that systems is in brackets is because we can't really design a FPGA that's mission critical without designing a mission critical system. So initially we're going to look at some of the challenges that we face to design these systems. We're going to look at some of the theory that's behind the theory behind safety criticality. We're going to look at some of the theory behind design architectures and design choices to get to a mission critical system. And we're going to look then at the architectural choices we can make in our FPGA, and finally we'll look at some of the more detailed FPGA techniques that we can use. So where do we need these systems? So we use these systems in a lot of areas, from aircraft to transportation to medical and process control. And obviously, as I was saying, it's only as good as the weakest part. So there's many factors that we need to consider when it comes to creating a mission critical system, and we're going to take a look at these over the next few pages. We're going to look at the environmental conditions that we face, the regulatory environment that we face, and hopefully we're going to explain a little bit more and make that a little bit knowledgeable. So the challenges that they face generally is when you talk about a mission critical system, a lot of people think necessarily that it means a harsh and ruggedized environment. That's not actually the case. It may be that you have a harsh environment when you're working on an aircraft or an automobile or even a satellite, but actually some of them could be in a relatively benign environment. It could be in an office-based environment, for instance a medical application, but it's still critical that it performs its mission criticality every day, because that piece of electronics could be keeping somebody alive, or could be monitoring somebody to ensure that they don't deteriorate any further. So it comes with its own challenges, not just based upon the environment. But let's take a little minute to have a look at some of the challenges that the environment can bring to us. So the first element of the environment that we need to consider is the temperature. So it has a very interesting effect on our silicon devices. Obviously at low temperatures things go faster, and at high temperatures things go slower. So when we need to design our systems, we need to ensure that we can get both worst cases, the low case and the high temperature. Now the low case can be interesting because it can mean that if we've not designed it properly, that we'll get things happening faster than they should. So we may get bus contention, we may get corruption. And at the high temperature, when things get slower, things won't occur. We may not register things correctly. We may miss transactions on buses, and that can cause issues as well. It can also cause an effect on power consumption when it's at low, when it's at starting up at low, when it's doing a cold start. We could see that we need a really increased power demand at the low temperature. I've seen this several times where we need to ensure that we've correctly scoped the the power supply solution to ensure that we can address any startups like that. And we also need to address other things such as oscillators. Oscillators, crystals, they may take extra time to actually start up and get going and be stable before we can actually use them. So we need to take into account that worst case time to ensure that the oscillator is up and stable before we move on. Now, one interesting aspect is that obviously we use a lot of highly dissipative devices, so in processors and FPGAs, and obviously like all ICs, they have a maximum operating junction temperature. Now this maximum operating junction temperature is what we don't really want to exceed in operation, but actually to give us the best reliability we want to derate from that. So the European Space Agency calls up a derating standard of 40 degrees C below the max rated junction temperature. So if your device is capable of operating with a junction temperature of 125 degrees C, then you will find that the European Space Agency's derating will say that can be no more than 85 degrees C in operation to ensure that the stresses on the device are reduced and we get increased reliability, which is what is very important to mission critical systems. So this brings with its own challenges, because we need to obviously take into account how we manage the thermal paths to keep these devices within the derated maximum if possible. So we can use conduction, so we can put thermal heat sinks on there. We can create thermal paths using the heat sinks to the base plate and the structure to pull the heat away. We can use radiation, but radiation is very, very difficult to use because it could be that you're not necessarily fully aware of where your equipment's going to be used. So your equipment could be sat next to another equipment that's radiating more heat than you, and as a consequence that equipment is heating you up. So in a lot of mission critical applications, actually you try to control the radiation that's radiated from the unit in a very controlled manner, such that you don't either radiate, and therefore you're not being warmed up neither by anything that happens to be close by. Now, convection obviously is forced air, is the circulation of air currents. We can do this via adding a fan into the system. The fan obviously will become a weak point because fans, it's a moving mechanical part, so it will eventually have a limited life. It will also require an opening in the system such that you could get contamination in there, such as water or sand or particles. So in a lot of high reliability systems, you see that there's not necessarily that many fans used, particularly if you're working in the spacey environment. You don't find many, although it is a really good interview question actually to ask somebody about how they would do it in a space application, and you can guarantee that somebody somewhere along the lines will say, oh, a fan, without thinking that there's no atmosphere present. So moving on to the next slide, we have the other challenge of vibration and shock. So vibration comes in many forms. It comes in three main forms, which are random, sinusoidal, and acoustic. So random occurs just from the interactions with elements. So if you're on a vehicle, for instance, driving down a road, the wheels interacting with the road will cause vibrations. If you're in an aircraft, the jet engines or the turbine will cause that. Sinusoidal vibration is slightly different in that is caused by anything that has a reciprocal or regular cycle. So things like a Stirling engine in a thermal imaging cooler, perhaps, or a turbo pump in a rocket engine will create sinusoidal vibration. The one that actually not many people always necessarily consider is that you can also get vibration caused by acoustic events. Now, what happens is in loud areas like jet engines taking off or rocket engines taking off, you get sound pressures that come out and they hit structures around there and they reflect back upon the vehicle itself, and that reflection back comes back and creates vibration, which is seen as random vibration by the electronics. So we need to ensure that we can do that. So a lot of times when we do random vibration at the low end of the vibration spectrum, we're also taking into account vibration that might occur due to the acoustic spectrum as well. Now, shock is a slightly different thing. It's a short duration, high acceleration event, sorry. And that comes in when we do sort of mechanical releasing or latching, or maybe somebody drops the equipment, and that can result in a failure. So we need to ensure that we can take into that account. So this, whereas temperature gives you more impacts of, you'll see sort of electrical failures, or maybe if you're very unlucky, you'll see things begin to get too hot and fail. In vibration and shock, generally when things fail, you see a very physical failure. You see the lid ripping off the system or a component flying off a board. But there are other areas where this has occurred. You say, many years ago, I saw a FPGA that was on a shaker table that was powered. It was going to be powered in launch, so it was powered on the shaker table, and it would keep locking up. And the reason it kept locking up while it was on the shaker table was that they'd used a one-hot state machine. We're going to be talking about state machines and how to protect them in a little while. But they'd used a one-hot state machine, and actually under vibration the bond wires were bouncing together. The state machine didn't have any protection on it. It was going into an illegal state and locking up. So our defensive design can actually take place in that as well, to ensure that we don't cause any real issues as we do the design, and we design our state machines, which I said we'll look at later on. So an area as well that we need to consider is EMC and ESD. So ESD is very much a system level electrostatic discharge. If we're lucky, we only have to deal with sort of the human body model and making that. If we're very unlucky, then we have to deal with the helicopter environment or something like that. But that's very much done at the electrical level, at the electronic level, at the board level, to ensure that any energy is dissipated to the chassis as easily as possible and doesn't propagate into the devices. EMC, on the other hand, is a very interesting challenge. And when we talk about this environment, I'm not talking about what we radiate, mainly I'm talking about what we're susceptible to. So we have to be able to deal with radiated and conductor susceptibility, because this can have an impact on our system, because we can't necessarily guarantee that the electrical world we're going to be interfacing in, everything's going to be within EMC standards or compliant. Things may fail and be radiating badly, or we may just be in a particularly bad area. So that can lead into the corruption of digital words as we transmit them, offsets in analog signals, or it could lead to, if we have a particularly poor set switch or reset circuit, it could lead to inadvertent triggering of that. So we need to design defensively to take into account that as well. Now, one that always excites everybody not sure why, but it always excites everybody, is the atmospheric neutrons. Now this results from cosmic rays, which are high energy particles, and when these strike the Earth's atmosphere, they collide with other atoms and they present in the atmosphere, and it creates a neutron and proton shower. Now what happens is these come showering down to Earth, and as they pass through our electronic circuits, it's possible that they can deposit sufficient charge in the silicon to actually flip the state, so flip a 0 to a 1, or appear as a transient glitch on a circuit line. Now if you're doing a space design, then there's much more to consider than this, and we'll mention it briefly later on. You know, there's things like single event latch up, single event burnout, single event gate rupture, which is not really what we don't really see this in a terrestrial environment at all, because they're not that high energy, but we do need to consider the bit flip. And what's interesting about the bit flip is it varies with both altitude and with latitude. So in some cases we can use the device manufacturer's own design tools to actually determine if we have an issue, because we can calculate the failure rate. So for instance, Xilinx runs what's called, I think, the Rosetta experiment, where they have numbers of different types of FPGAs at different altitudes around the world, from sea level in New York City all the way up to the tops of some mountains in the French Alps. And I think Denver is another location that they have some. They gather statistics on SEUs and they calculate the fit rate from that, such that you can actually determine the mean time between failure of this occurring. And you know, for many applications, if you're ground based or what, once you've calculated it, as long as you're going to power cycle the equipment fairly regularly, and that may be every couple of months or something, then you don't have to worry about it. If you're in an aircraft, if you're flying, or in a really high reliability application, then we do need to consider it. But you can do the calculation, and the tools are all there to allow us to actually do it. So to help us to address some of these challenges, there are a number of standards that are present in the world. So perhaps one of the most famous ones is 61508, which is an electrical functional safety specification. Now there's also a number of sub-specifications that have come from this, very specifically industry dependent, so they go from railway all the way down to automotive. For a lot of aerospace applications as well, there's DO254 and 178, but a lot of the techniques we're going to talk about are very similar. And just to keep this simple and not take it on for 2 hours and only 1 hour, I'm going to particularly focus on IEC 61508. So IEC 61508 defines a number of what are called safety integrity levels. It actually defines them in two types. It defines one called continuous operation, where the equipment is operating continuously, and one called on demand. So we're going to look at, for the applications, we're going to look at the continuous operation one. So what you can see here is there are 4 safety integrity levels ranging from 1 to 4. 1 is obviously the lowest and the easiest one to achieve, 4 is high. So if you look at this, then to achieve a SIL 4 system, you need a time to failure of 100 million hours, or its reciprocal of 10 fits. Now just to give you some context, a modern FPGA may be around that number of 10 fits, maybe slightly lower depending upon the process node, maybe slightly higher depending upon the node as well, but it will be around that number. But that doesn't include the oscillator, the power supplies to power supply it, the board that it's connected on, the solder joints, or the system. So the actual system, you know, would have a failure rate much higher than that. So it's very difficult to actually create a well architectured solution for the higher SIL 3, SIL 4 levels that demonstrates this failure in time, and we're going to have to use redundancy, hardware fault tolerance, and good design techniques to achieve this. So one of the areas that we use to achieve the SIL level, as well, is to define how many of the failures that the system can actually detect. So what we need to be able to do is we need to be able to detect the majority of failures in the design. So this is called the safe failure fraction. So a safe failure fraction occurs if we can actually detect it. So it's okay to have a failure that may be dangerous, as long as we can detect that failure and the system can take appropriate action before it becomes dangerous. So the safe failure fraction is the total number of failures within the system that can possibly exist as a ratio against the number that can actually be detected. And depending upon this, you will see in the chart on the bottom there as to where for each SIL level, whether you need to have a hardware fault tolerance of 1, which is there are 2 channels, or a hardware fault tolerance of 0, where you don't need any hardware fault tolerance, or for the higher levels, obviously you can see that you need a hardware fault tolerance of 2, which is at least 1 out of 3 circuits functioning. Not quite TMR because we're not voting, but it's hardware fault tolerance. So to achieve this, to achieve this early failure fraction, we perform what's called a FMEDA, which is a failure mode effects and diagnostic analysis, which allows us to run through the design, look at the failure types, the failure rates, and actually work out how many of these failures we can actually detect and monitor to go into the safe failure fraction versus how many we can't. And then that begins to drive how many of these channels we need, whether we need a HFT of 1 or 2. But obviously, if you're setting out from day one on this, you're going to be looking at this and you're going to be thinking, you know, it's very challenging as an engineer. You apply your engineering judgment, so you think it's very challenging for a SIL-free system, for instance, to be implemented with no hardware fault tolerance. Therefore, a safe assumption would be in your design to include a hardware fault tolerance of 1 and assume that you can get 60 to 90% of the safe failure fraction in there. If you're going for a SIL-4 solution, then probably the more sensible solution is to start off with a hardware fault tolerance of 2. Because that's such a challenge to achieve there. So we mentioned this slightly, and we were going to talk about the failure space a little bit. So of all the failure spaces, there are 4 types of different failures that we can have. We can have the safe detected, the safe undetected, the dangerous detected. The big concern, the one that goes towards the charts on the previous page that show why we have the additional hardware fault tolerance, is the dangerous undetected, because we can't allow the dangerous undetected to actually occur, so we need to put in hardware fault tolerance to protect against those. So, you know, an example of a safe undetected one for those, maybe a decoupling capacitor failing open circuit. It's probably safe because we have plenty of decoupling on the board. We'll never see a change in the system, and it will continue working. Whereas a dangerous undetected one, maybe we couldn't correctly determine the separation between 2 events, and if we can't correctly determine that determine the time between the 2 events, then we have a problem and we could fail dangerous. So therefore we would implement hardware fault tolerance to ensure that that event can't occur, because if the first circuit fails, the second circuit picks it up. So looking a little bit more at the hardware fault tolerance, so it's defined generally as 1 hour 0, or 1 hour 002, or 1003. So what this really means is it's not kind of the 2 elements voting together. So what it means is that there is 1 hardware element for 1 out of 1. So 1 hardware element, and that 1 hardware element needs to work. Fairly straightforward. For a HFT of 2, there are 3 hardware elements and only 1 needs to work. So you can work out the hardware fault tolerance by taking the M as m minus n. So if you have m x n, it becomes quite easy to actually work it out. And it may begin to look like actually that the hardware fault tolerance is giving you a relationship to redundancy. Now that's not quite true, because as you start looking at more complex structures, say if you had 2 out of 4 channels that needed to be working, then you know that you have redundancy, but you're not quite sure how much, and to generate that you need to generate the reliability block diagram. What you can say is if you have a hardware fault tolerance greater than 0, you have redundancy. You just need to do a little bit more, you need to do some analysis to actually work out what that redundancy actually is. So let's take a little look now at a little bit more at the theory side of it. So one of the questions I ask a lot of people at interview actually is that if a system has a mean time between failure of 1 year in hours, so 8,760 hours, does that guarantee that the system will operate without an error for that entire year? Actually, a lot of people will say that it does, but actually it doesn't, because mean time between failure doesn't give you the probability of success or the probability of failure. How we calculate the probability of success and then the probability of failure is we need to take the mission time in hours and divide that by the mean time between failure of the unit that we've calculated, and plot that exponentially. So when we plot that, we will see that if we have a probability of success for 1 year, an MTBF of 1 year, that we have about a 36.7% chance of that still working at the end of that 1 year period. At about the 6 month period, that's about a 0.6%. A probability of about 0.6 of it still working. So it's quite a challenge, and this is really important to understand because it maps back to that SIL slide on the first few pages where I was showing the 100 million hours. You know, that to get to this, you know, we've got to that essentially is the MTBF, and that becomes quite a challenge to ensure that to ensure that we get there. And the other thing to think about the mean time between failure is that it's only valid in the constant failure rate period, which is the bottom of the bathtub curve that I'm sure we're all aware of. So during the initial infant mortality, the failure rate, the MTBF, is not valid, and that's the same as well on the wear out side, on the back end of it. So normally, to get into the constant failure rate period, a manufacturer will perform burning to try and take out any infant mortality in their components that they give you. And as a system manufacturer of mission critical systems, you will probably also perform burning to try and remove any infant mortality that may be in your systems, or any weaknesses that have crept in from manufacturing. And how we can work out where we are in which of the three elements comes down to the fact that we can do a Weibull analysis to actually determine from the beta coefficient actually where we are in that, as to whether we're in the infant mortality, the constant failure rate, or the wear out period. So to calculate this and to support all this, mission critical systems come with an awful lot of documentation. A lot of aircraft designers joke that when the weight of the documents equal the weight of the aircraft, then the aircraft's good enough to fly, and they're not far wrong in a lot of cases. So we're going to do some simple things to support this. We're going to have some documents behind this. So we're going to have a preliminary hazard analysis. Now this is going to define all the hazards, the dangerous failure modes that may occur in our system. And then we're going to ensure, obviously, that our system cannot achieve those. We're going to use fault trees, which is a top-down analysis of the failure modes. We're going to look at the FPGA, which is very similar, a bottom-up approach. We may do a part stress analysis, which looks at the part stresses on the components to ensure that we're not stressing them too much, either thermally or electrically. And we will look at elements such as the functional hardware assessment, independent protection layers, and layers of protection. Now another thing that we will look at is the part quality. We're going to talk about this in a little bit more detail, but we can buy better quality parts, obviously, but we're trading off for those better quality parts, we're trading off expense as well. We can do derating, which falls into our part stress analysis, so we can apply electrical and thermal derating stresses to our components to ensure that they're not all being run at the maximum to reduce the stresses on those components, increasing reliability. And we can do worst case analysis. Now worst case analysis is we look at the design and we run through the design for all its worst case possible conditions. So we really try to make sure that this design takes into account all component tolerances, all component drift, all component aging, all component radiation effects if it's going into space, and looks at the worst case conditions of those, and proves that across the entire operating range the circuits can work, and that they will work properly, and that there will be no damage. Now we may even do if we have two boards, it may be that we simulate one board at its maximum worst case and the other one at its minimum worst case, to ensure that when they're biased like that, they still actually communicate and talk to each other reliably, and we don't introduce any problems that way. We also need a quality system as well, actually, to implement, to tell us how to actually design, manufacture and assemble these mission critical boards, and that quality system is going to be aligned with an international quality standard such as AS 9100 or ISO or the ISO standards. And then as well, we will also have internal design rules that tell us how to design our boards, how to design our FPGAs, how to design our SoCs. So they will go down to the level of code rules. So when it comes to the failure rates of the components that we use to go away and calculate the mean time between failure and the probability of failure in hours for the SIL, we need to have some sort of reference material. So a very common reference material is MIL Handbook 217, although there are some issues because it's not been updated for many years. But when we look at this and we run it through, we see that the electrical stress identified by the part stress analysis comes into play, the quality level comes into play as defined by the application or customer, the temperature comes into play, and also not shown here, but actually the environment comes into play as well. So whether in MIL Handbook 217, whether it's in a ground benign or a ground mobile or an air launched missile, and that will have a number of factors that come into this to calculate the reliability of the circuit and of the system. So when it comes to component quality, we have the standard devices. We can buy commercial components; they're the cheapest ones possible. They're these days they're really good. I can't remember the last time I ever had a standard component fail on me, really, as long as you've taken suitable care and practice with it. You can buy them with extended temperature ranges, or you can buy them with an industrial temperature range. Now, if you're in a really demanding application, then you can perhaps consider buying a military or a space grade component, so one that aligns with QMLQ or QML or QMLV. Now, once you start with the QMLQ and QMLV, then the price of these components go up because they're produced in smaller batches. They have much more rigorous testing done on them to ensure that the quality of that component is absolutely maximum and will give you the best performance possible in the end circuit. So just to wrap up the sort of the theory side of it now, a really simple flow is that we can to calculate our mean time between failure and our SIL level is that we can perform a part stress analysis, we can perform the FMEDA using the part stress data, taking into account of the hardware fault tolerance, we can take into account the ground benign environment and such like, the MIL standard 217 environment, its failure rates, we can use that to calculate all that, and then we can create a SIL verification report, we can calculate the probability of failure in hours and the safe failure fraction, and from that we can get to the SIL level that we're at, and then hopefully our independent accreditor as well is also going to agree that we have achieved that. So when it comes to looking at these, we're really looking and trying to protect against two types of failure. The first one is systematic, which arises from something that we've done in the design or manufacturing, and the second one is a random failure which occurs due to stressors or aging or the environment. And now random failures can be one of two things. They can occur because of a permanent fault, such as an input on an FPGA gets stuck at a level, or it could be a more transient fault, such as a single event upset flipping a bit in a memory. So we need to be able to address both systematic and random faults, and how we approach this is going to be slightly differently. So we also need to take into account a holistic approach as well when we come to do this. We need to look at our hardware and software design, and we need to see the interdependence between the two. So you can see that the hardware architecture enables the hardware enables a tolerance and avoidance of hardware faults, but it also has an impact on software's ability to tolerate faults as well, and how software is architectured will also have an ability to tolerate hardware faults. So it's a very holistic approach is needed when we first start out down this route and start looking for what we can do to actually create a very mission critical system. So let's take a look at some high level considerations. So one of the first things, actually, this is really important to me, it's a real personal favourite of mine, is we need a strong engineering governance scheme. And that strong engineering governance scheme is going to apply an engineering life cycle that tells you how to go from concept all the way through to disposal and end of life. And throughout that you're going to have a number of engineering gates such as kick-off reviews, system readiness, system requirement reviews, system design reviews, preliminary design reviews, critical design reviews, test readiness reviews, manufacturing readiness reviews. And we're going to have a whole host of these reviews, and these reviews are going to be in detail. They're not there to pat you on the back and tell you that you've done a good job. They're there to catch out why you've not seen the wood for the trees in some instances, and to make sure that the sufficient engineering due diligence has gone in to enable you to progress from one stage to the next stage. So you really need an independent panel of this. Now each of the stages will be made up of phases and processes and procedures, and we'll take a little bit of a look at what they are on the next few slides. And so when it comes to engineering governance, if we look at if we're designing an electronic module, we may be at the preliminary design review stage. And within that electronic design stage, we will have done a schematic design as a process, we will have done a PCB design, we will have PCB manufacturers review it and PCB test, and we will have applied things like D-rating, schematic rules, DFM rules and PCB rules. So all this collates as evidence to go into our preliminary design review that we're ready and that we're good to take this forward, and that we are mature enough to move from one position to the next. This will occur several times throughout the engineering life cycle, and it's really key to ensure that we have a good quality of results and a good quality of systems, that we have a strong engineering governance culture. So the V model is also very interesting as to how we're going to do this. So we start out at the very top with the concept of operations, the concept of operations, and then you take the concept of operations, you generate your first sort of high-level system requirements, and then from those system requirements you can generate subsystem requirements, from those subsystem requirements you can generate equipment requirements, and from those equipment requirements you can generate hardware requirements, software requirements, FPGA requirements for a particular unit. So when we work as FPGA engineers and hardware designers, we're predominantly at the bottom of the V, and each one of these maturity flows down. So as we flow down, so these gate reviews, as I mentioned, as we flow down. So as we flow down, we should be having a preliminary design review, for instance, of the high-level systems, the concept of operations. A PDR, having that completed should then allow a PDR at the systems requirement, and then the subsystems requirement can also have their PDR. And then finally, once all the others are mature and have flown down, we can do our design, and we're in a position to hold our PDR. So on the initial side, on the bottom of the V, sort of the verification, the requirements flow down. When we get to the bottom, it becomes a bit of going up the V. It becomes a top-driven process, because we have a bottom-driven process, because we have to go. We need the evidence from the stage below to prove that the stage above it is mature. So you go up from CDRs. You have a CDR at the lowest level, then a CDR at the equipment level, then a CDR at the subsystem level, then system, then user level, and each one of them builds on the evidence that's come before it. So this is really important that we understand this V, and particularly how the requirements flow down, all the way from the concept of operations that the user creates all the way down to the bottom. So when it comes to this, we have a number of elements in the process that we can look at to do this. So we have the requirements to define the function, the availability, the operating life, its environment. We have the system, which will define the architecture of the system, the units of it. If it's mission critical, the single points of failure, the interfaces, the telemetry. We have the hardware architecture that we will consider with the routing and the switching, the module interfaces, ensuring that there's no failure propagation. And then we have the hardware design, the FPGA design, and the design analysis. Now, this slide is one of the best slides that I can think of. Actually, I've seen this time and time again at several companies I've worked for, in that if you don't have time to gather the requirements and get those signed off and approved and working for, then really from day one you've got a lot of trouble, and you're going to spend a lot of trouble on the back end of that project, not only trying to work out if you've built the right, if you hit the requirements and that your requirements are right, because you don't know what they are or they're rapidly changing, but also if you built actually what the customer wanted, and the customer expectation could be different. So to give some idea of the requirements that we may have, we will have identification of stakeholders in the project, and that's just not the customer, that's also regulatory stakeholders such as the people like ESA, NASA, FAA, the FCC, regulatory bodies that are going to be signing this off. We have internal stakeholders in terms of design, manufacturing and test. And then we have obviously the creation of the specification tree, and then the flowing down of the requirements. Now, one thing that's very important actually is that requirements should always be able to be traceable back. So from the highest level of the system, the highest level system requirement, we should be able to trace all the way down to a low level requirement. Or if we're looking at a low level requirement, we should be able to trace all the way up to that top level requirement to find out why that requirement exists. Because that traceability is very important when it comes to defining critical systems, and particularly mission critical systems that are going to be certified, because it defines why that functionality is currently there and presently exists in the design, and ensures that people haven't just gone away and put in functionality because they think it's a good idea at a particular level. So the requirements will contain a number of things, such as the system lifetime, its operating environment, all the functional and the non-functional requirements. We also need to make sure that requirements are written in a sensible, smart manner. So what that means is we will use the standard terms and requirements such as shall, should, would and will, and we will use those, and we will write requirements that only have one requirement, per requirement. So as funny as that sounds, some people put multiple requirements in there. It shall be painted green, and it shall be capable of operating over 20 degrees. They can't be one requirement, they've got to be two. And you've got to make sure that the requirements are also achievable, that they're smart, measurable, and we can actually work out what they are. So when it comes to the more traditional requirement flow, not a model-based requirement flow, when it comes to traditional requirement flow, we're going to have the sort of the high-level stakeholder requirements that are going to have their stakeholders come in. That's going to be trace down and create some system requirements, and then we have the lower level requirements below there. At each level we will have defined or derived requirements coming in. But as you can see in this diagram, each level traces, not only flows down to the level below it, but it also traces back to the level above it. Now we also have a compliance matrix at every level, where initially we can say whether we think we're going to be compliant or not, and then we can raise requests for deviations, and as we get towards the end and we've got our verification evidence and we can say that we are or not compliant, then if necessary we can request for waivers can be raised as well. Now at each level we should also have a victory which tells us how we're going to test these requirements. So is each requirement going to be proved by test, analysis, inspection, but how we're actually going to prove that requirement, and that then goes into creating our test specifications for that level, and helps create us that nice overall picture of an integrated requirement package, verification requirements that trace all the way through to our test specifications. Now our interface, our requirements might also reference other documents such as standards, or what are called interface control documents that define how the interfaces are between the modules. But that's a very complex requirement picture that we have there, and it's really necessary for when we do mission critical systems. So this is a famous graph from Incosi, but it actually shows the number of requirements against the number of man hours that it takes. So we need to be very careful with this. You know, if we the more requirements we put in there, the longer it takes to verify each of those requirements and to generate the evidence for each of those requirements. So we need to be very careful about the number of requirements. So it comes back to what I was saying earlier on about having smart requirements and only having sensible requirements in there. You know, we need to really ensure that we do that. So when it comes to the system level, when we look at the for an electronic box, this is more normally the sort of the electronic system level, really, not the system of systems. But this is sort of now getting into the architectural level of the electrical system. So maybe, you know, at this level it's going to introduce the architecture of the solution, whether we have redundancy, and whether that redundancy is inter or intra module. So do we have two sets of redundant circuits on the same circuit card, which is intra-module, or do we just replicate the module twice, inter-redundancy? And how do we do that? How do we run those in terms of the redundancy scheme? Are they hot redundant or cold redundant? So with hot redundant, the redundant system is powered up, it's seen the same inputs as the primary unit, it's ready to go, and the switchover, should one fail, is seamless and instantaneous, and you don't see any downtime. If you have a cold redundant system, then the redundant system is powered down. So should the primary redundant fail, it takes time to commission the second redundant unit and get it up. Now you might all be sat there thinking, hey, well, obviously then hot redundant's the way forward, but actually cold redundant actually ages a lot slower than a redundant system that's powered up does, because if it's powered up, it's aging at the same, it's under electrical stresses, so it's aging at the same rate. So for instance, if you have a satellite, you may prefer in some payload applications to have a cold redundant system as opposed to a hot redundant system. So we also need to look at this electronic system level. We need to look at the equipment interfaces, whether we have a single connector or multiple primary redundant. As I mentioned, we need to look at the dangerous failure modes and whether that failure can propagate such that it can't propagate outside the unit and it can't have a knock-on effect outside the unit. We need to look at what sort of telemetry and event logging we're going to do, such that we've got the health monitoring. And we need to look at critical applications and critical command sequences as well, to ensure that we can't inadvertently issue the wrong command. And for things like links, we need to look at the acceptable bit error rates and whether we need to put things in there like error correcting data on RAMs and on configuration memory. So let's take a look at redundancy first. Very similar to hardware fault tolerance, only it's at a higher level. So we could have a simple module where we have an input and output, but to get a SIL4, that's going to be very difficult to achieve. So maybe we introduce a second module B and have that as redundant. Now when we do this, we need to make sure that the inputs going into module A and B, that module A can't fail in such a way that it prohibits module B from seeing the input because it's corrupted by a failed module A. And the same for the output. We need to ensure that should one unit fail, it can't prevent the other one from controlling that output. So the sharing of inputs and the sharing of outputs between the two modules becomes a very challenging area of the architecture, and a very challenge for the electrical architecture teams to do. But we can do it. Now obviously this comes with an impact in terms of introducing redundancy, comes with an impact in terms of not only size, weight, cost and power, but also it comes with an impact in terms of probability of success, because it greatly increases it. But it also greatly increases your size, weight, cost and power as well. So it's a very architectural level thing, it's a very high level decision to be making as to how you're going to implement this. Now what we need to do when we introduce our redundancy as well is if we need to work out whether we need the system to just fail safe, such that we detect a failure has occurred in a module and we just shut down and go to a failed safe state such that no operation can continue and it can be repaired, or if perhaps it's in orbit or flying in a plane or something, then we need to be able to continue the operation of it such that it doesn't really see the fact that it's occurred. And like I said, I've talked about the active and the cold spared redundancy, but one of the benefits I said of cold spared is that it ages at 1/10 of the rate of the active redundancy. So that's very useful in applications which have got a very long lifetime. So if you've got a 15-20 year mission, then you want to ensure that you have got the best redundancy scheme selected. So when it comes to redundancy as well, and for hardware fault tolerance, we need to remove as many common causes of failures as possible. And within electronic systems, there's numerous ones that exist. So obviously power supplies and sequencing, we can't power redundant modules off the same power supply, because if that power supply fails, it's a single point of failure. Same for clocks, resets, memories and configuration memories. Now I/O interfacing becomes difficult because you need to ensure that the failure can't propagate from one module to the other module using that interface, or that your module, the failed module, can't necessarily take out that input and prevent it from being used further. Now what's used in some areas is diversity of components as well, in that you will use components from different batches just in case there's a manufacturing impact with that batch, or maybe you'll even use devices from different sources, or even different manufacturers, or completely different technologies to implement those redundancies. So when it comes to connectors, we can have a single connector between module 1 and module 2. But if we get an error in between there, then cables fail, then the system's down, the communication's gone. So what we can introduce is we can introduce a point-to-point prime redundant connector, and we can have two cables in between the modules. And such that if one of these cables fails, we can still use the redundant channel, and that works well. Now this is really good, but it does come with a hit, because what about if we split modules 1 and 2 into having redundancy as well at the module level, in which case we would need to have a fully cross-strap primary redundant connectors between each of the redundant modules and each of the cables. So this would come with a real significant weight impact and a cost impact, but if it's a very critical application, then it should be considered. So when it comes to looking at some of the error correcting codes that we can use as well to protect our memories and data as it's transferred about the system, we can obviously use a simplest one, which is a parity error, which can detect it, or a CRC or a MMM code, and they're all very good at detecting errors. Or we could use a code such as BCH or Hamming or Reed-Solomon to not only detect the error but also to correct a single bit error and actually keep on running and keep the system going and alive. So one area that comes into this is with the safe failure fraction as well, and with the tests that I was talking, with the systems that we were talking about earlier on, as to how we're actually going to know if we're failing or if we're in a good situation or not, is we can put in what's called built-in test. So a built-in test enables us to see the status and the health of the system. So we can have a power on built-in test, run one powered on, just like your PC does, to make sure that it's suitable for applications and suitable for the application at hand before it moves on to the next one. We can then have a continuous test, which is running slowly in the background, testing a few key parameters, not interfering with the operation of the circuit at all, or the system at all, but actually just running and maintaining and monitoring the health there. Or we could have a on-demand bit, which would run on demand before critical applications and test much more of the hardware to ensure that all the paths necessary for that particular application are present. Now this is where really the new FPGAs come into their play, because they have, and the SoCs like the Ultrascale and the Zynq come into play, because they have the inbuilt XADC sys monitors in there that allow the junction temperature and the device supply temperatures to be, device supply voltages to be measured and actually logged, and we can set alarms such that we can take action if they go too high or go too low, so we can do a little bit of prognostics in there as well. And we can also pull through up to 16 external inputs as well, so we can have a very complicated, very complex, very powerful built-in test and monitoring system with a very low overhead on the design. Now these are some of the parameters that we might want to consider in terms actually the sort of temperature, currents, voltages. And if we're looking at the sort of redundancy switching where we have prime redundant, we may want to look at the current status of the redundancy switch so we know which channel we're feeding off. And we may want to look at the results of processing as well. So if we're doing a radar application, for instance, we may want to inject a false target at a certain specific range and altitude such that we always know it's there. If you don't see that, then you can see that there's something wrong with the processing chain and then the system can take the appropriate action. But these are just a few of the things that we want to do, and maybe actually some of these actually, depending on your application, you want to log these to a non-volatile memory such that should an event occur we can actually go in, get that at non-volatile memory and actually take a look at what's in there and what happened and understand why the unit began to fail. So one of the more common approaches as well is to have an arm and fire approach if we're sending commands across a bus, because in an electrically noisy environment, we don't want a single command, say to deploy a solar panel around a satellite, to flip inadvertently from a hello world or a simple connection request and actually turn and fire that explosive bolt that deploys the satellite due to an error. So this is where you use an arm and fire command. So essentially you issue two commands, one that says get ready and one that says go. And if there's a timeout between the two, if you don't see if after you've issued the get ready you don't see the go command or the fire command, then you time out, or if you see a different command then you just abort the sequence and go back to where you were. This prevents inadvertent operation of really highly critical applications from doing so. It provides a second path essentially. Now what we can do as well when we create these command words that are flying about our buses and our communication links is we can make sure that we use a Hamming distance of at least 2 between the critical commands, such that you can't turn one command inadvertently into another one. You can turn it into a command that's not recognised, but that's better than turning it into a command that is actually recognised, processed and accessed upon. So in this example here you see that the arm and the fire command, they would need to both change 2 bits to change from one command to the other command. So there's a Hamming distance of 2 in there. So finally the bit that we've talked about the sort of the architectural side of things, we've talked about the theoretical side of things, what SIL is, why we want to do it, some of the challenges of the environment, some of the high-level architectural decisions at the system level that we can do, and now we have some FPGA design techniques that we can use to implement them. So obviously the first one is we need to make sure that what we put into our tool chain is what we get out. So we don't want the synthesis tool or the compiler adding in extra logic unnecessarily that changes the functionality of it, because we can't really verify that, or we can, but it's very difficult to verify that. So to ensure that we can use certified tool chains, so there are 3 tool chains, 3 levels of tools that become certified depending upon where they're used in the process flow. So it's either whether they actually generate a direct output, generate the code, or they're used in verification or test. Now the next one is, it wouldn't surprise you to know, I'm sure, that there was at least one satellite flying about that had some problems because it had problems with its clocks going into its FPGA, because they'd not considered the oscillator startup time in the design analysis. So we need to carefully plan this, obviously very carefully use the global clocks and the local clock resources, and be very careful about ensuring that if you're crossing a clock domain, that we cross it properly and safely and do sufficient analysis on it to prove that it's safe to do it. Now we also need to ensure that any asynchronous inputs are synchronized to the specific clock domain. So that is within the FPGA and internally to the FPGA. So the resets, again, there's been a few issues with resets flying around in orbit in satellites as well, in that they'd relied upon the power on state, the default power on state. And as such, we can't do that, So for critical aspects, we don't want to ensure that we're just going to rely on it powering up in the right state. We want to actively drive it to be in the right state, which is why it comes with the reset. So with a reset, we want to do an asynchronous assertion, such that as soon as the clock is up, as soon as the power supply is up and running, as soon as the FPGA is up and running, we can assert that reset to give the oscillator time to start up if it's not already started up, and to make sure that the rest of the system is coming up properly before we deassert it. Now when we deassert that reset, we want to ensure that it's done on a synchronous clock edge, because we don't want to cause any metastability events in the clocking domain. So we need to ensure that we deassert it synchronously to the clock domain we're in, and we don't violate any setup and hold times. And we need to obviously ensure that any outputs are reset to deassert peripherals, such that we don't get contention, particularly on bidirectional buses. So we talked about this a little bit earlier with the atmospheric neutron, and this is really a slide from my days in the space industry, which shows the different types of single event upsets. You can discount the destructive ones from this element in the terrestrial environment that we're in, but you have the single event latch up, where it can latch up the device and take more current. That's not likely to happen on the ground, but we have the single event upset, multiple bit upset, and the transients as well. So we need to consider some of these within our design. And how this can work is, so we can have some issues with things like state machines where we can get a bit flip. So if you look at this example here, we have an idle, a read and a write state machine, and they're quite happily cycling around the three states, doing reads and writes all day long. Now, if a bit flip occurs from a valid state to another valid state, that's just an incorrect state transition. And while it may change the functionality of the design, that can be mitigated for at the higher level, but we can pull that through and we can carry on doing that. If actually the bit flip occurs and flips us into a state that is unmapped, then we're locked in that state and we can't recover from that without power cycling, which is quite embarrassing if we're in an aircraft or something. We need to make sure that isn't the case. So we need to be able to recover back from that idle state. So how we can do this with state machines is there's a number of options that we can do. The first question we should always ask ourselves is, do we really need to do this or not? If we don't need to do this, then fine, we can just carry on as we normally would with a normal state machine. If we do need to do this, then we need to work out whether we need to be able to just detect the fault and stop and fail safe, or whether we need to carry on processing such that a fault doesn't occur to us. So let's take a look at detection first. So if we're going to detect it first, it depends on whether we have a synchronous, a sequential, or a one-hot state machine. If we have a sequential state machine, there are a few techniques we can use. We can map in all of the unused states, shall we say, and then we can, after power on reset, we can cycle through each of the unused state from one unused state to the next until we get to the idle state, such that if we go into an unmapped state again, we will bang back. We will just come back into the idle state eventually after transitioning however many unused states there are. Now again, that will change the functionality of the circuit, but that can be mitigated at the higher level because the state machine's terminated early. We can also look at the state machine, and we can also get the state machine to preserve the unused states such that we take specific action in the unused states. Now, because there's no path into or out of that unused state, for instance in this example, we would need to maintain and use synthesis constraints to actually stop the synthesis tool from optimizing those out. The third one is we could use a Hamming distance of 2 for the state encoding, such that the state machines can't be flipped from one valid state to another, but they can go into an illegal state, and again in that illegal state we can address it. Now, if we've implemented a one-hot state machine, like I was talking earlier on the shaker table, the vibration table, then what we could do is we could implement a parity bit, because there should only be one bit hot at any one point in time. So we can implement a single parity bit to actually monitor that entire one hot state machine. And if we see 0 set or more than 1 set, then we know we have an issue, and we can take it from there. Now, if we need to keep operating, then we have two options. We can implement 3 of the state machines in TMR and actually vote on the outputs of the state machines, or we could implement something using a Hamming distance of 3 between each states and then map in the adjacent states. So we're going to look at TMR in a little while, but let's take a quick look at what mapping these in with an adjacent state of 3 is. So what this means is that if we have a Hamming state of, say, 0, 0, 0, then we also have 3 adjacent states that can be achieved by each bit flipping you into. Now, if we know this, we can encode the states correctly with the correct Hamming distances, or we can create the adjacent states as well, and then we can create our VHDL or Verilog to actually run through this and prove this. So what this looks like if we were to create a package that looked like this for a state machine. So you can see we have the 8 states defined down there. Each of the states is defined by a Hamming distance of 3. Each of the states has a Hamming distance of 3 between them, and I have a Python script, if anybody wants it, that will actually go away and take a normal state machine and regenerate it as a state machine with a Hamming distance of 3 and with the adjacent states mapped. Underneath state 8, you can see the mapping in of the 6 adjacent states that exist. So we have 6 adjacent states because we have 1, 2, 3, 4, 5, 6 register bits. So for each element for each register, we have a number of adjacent. We have that number of adjacent states for that one state. So each one of these states will have 6 adjacent states. So what this looks like within the RTL is we can say if we are currently in state 1, adjacent 2, adjacent 3, adjacent 4, then perform this action, and that will allow us to keep on running. Now, crucially, when we change states, we always need to change state to the correct state and not an adjacent state of it. So we need to change state to state 2, state 3, or state 1. But implementing it in this manner allows and ensures that we can keep on running round, and that the state machine will keep running, and that we won't see any impacts from that. So another area actually that can cause some issues, and that has caused some issues in flight as well, is the terminal count of a counter. For instance, so if we do if count equals 9, then. But what happens if we get a bit flip due to noise or an SEU that flips a bit in that counter over and it becomes 11? Well, then that won't run, and our circuit and our design may lock up. So what we could do actually is we could look for greater than or equal to. Now again, we detect that it's gone to 11, so we take the appropriate action. But we may have got a shorter count than expected. So we would have to address that at a system level. So we'd have to address that with TMR or some such thing. But at least we're not in a situation where we lock up, but we're in a situation where we can recover, where we can recover from it. Now, if we're using a certified toolchain, this shouldn't actually happen. But actually, we also need to consider some of the synthesis options that can occur when we run. Because in this example here, it's possible in the original code, it's possible for Q and not Q to be true at the same point in time. However, with the implemented code that came out of the synthesis tool, it's possible for Q and not Q to be true at the same point in time if there's a noise or a single event upset. So we need to consider the downstream effects of what Q and not Q are attached to, and is having those both set at the same point in time going to be an issue or not. So we need to just be careful of synthesis constraints and stuff. Now, we've all heard of triple modular redundancy. I've mentioned it a few times in this talk, but there are many different methods of doing TMR. So the first one is global TMR. So global TMR, we triplicate everything within the FPGA in its entirety. So we take the entire design and implement it 3 times in FPGA. We implement the I/O pins 3 times. We have 3 separate clocks. And we have 3 stripes of the design. Now that comes with a real area penalty, because it reduces the size of the design that we can implement in the FPGA, because it reduces that FPGA significantly. You don't just get a third, you get much less than a third. But in theory, it protects the design against everything, apart from the actual FPGA failing or something like that, which you would address with your redundancy scheme. But it comes with a bit of a problem in ensuring that the validation of the final bit stream is as we desired, and it's going to have an impact on power as well, because obviously we're powering 3 times as much logic in the design. So if we look at what this looks like in the FPGA, you can see there are 3 streams: a blue, a orangey colour, and a green one. And you can see that between each stage there are 3 elements of this. Now what this shows is that we also synchronize between the flip-flops at each stage to make sure that any errors in the TMR get resynchronized. Now when we floor plan this within the FPGA, we need to ensure that there are very physical elements, and there are very physical elements separated from each other, as you can see in the diagram below. Now that doesn't necessarily show the crossing, because we need to be very careful to ensure that they only cross and talk to each other when they should, to resynchronize those flip-flops. So this is just a simple synchronization flip-flop circuit that's used in a lot of applications to show how you can actually do that across the 3 elements. So this is the virtual element, is the only element that you want sharing the data, or sharing across the 3 instances of the IP cores. Now with large grain TMR, it's very similar to global TMR, only actually we throw away the synchronization of FPGAs of registers between elements, and we just do it once at the end. So it still comes with the same power, the power and performance, the performance capability hit on the devices, but it gives us a little bit more simple to implement. So you can see there, you just have the three streams and the final voters, and then this is what the FPGA application implementation looks like on the end, with the final row of voting. And then finally we can have the local TMR. So this is what you find hard embedded into a lot of very specialist devices. So they will do the TMR. They will do the TMR on a register by register. They will have 3 D types and they will vote on it, and then it will go on. Now the problem with this slightly is that as you get faster with your clock edge get faster, if you get noise on or glitches on the combinatorial logic or single event transients on the combinatorial logic, if it occurs at the wrong point in time, it can get clocked in. And when it gets clocked into all 3 flip-flops at the same time, so as you can't detect that an incorrect event has occurred. Now there are things that you can do. Some devices use temporal filtering, such that they offset the clock used for each one of the flip-flops, such that the likelihood of clocking in all 3 into a single event transient is reduced, and then that protects against that one. But so the global and the local TMR, global and the large grain TMR, are much more likely to be implemented by the designer, for instance, whereas something like the local TMR is much more likely to be implemented in the FPGA logic itself. So obviously we've gone through our design. We have our state machines, we have our counters, we have our signal, we have our data flow, we have everything that we want in there. Now we need to consider the verification, and we've got to be very vigorous when it comes to verification, because we need to test that all the behaviours and the potential failure modes of the UUT, we've tested them, we've stressed them, and we've made sure that it behaves exactly as expected. So what we really need is an independent person from the designer to write that test, to do that testing, because sometimes, you know, we can't see the wood for the tree, so you need that. Now what we should do as well is we should have a document that defines the test strategy that we're going to do. So if you remember back to many slides back now to the requirements flow down, we had the requirements flow, the test spec, and the test specific, the Vickery and the test spec. So we should have a test specification for each element of each module of the FPGA, saying this is what we're going to do, this is how I'm going to do it, and that should be peer reviewed and signed off as well. Now one of the things we look at when we do the UUT, obviously looking at the unit under test, is we want to ensure that we hit all the corner cases and boundary conditions. And that's very important because we need to really stress test these systems to make sure that we hit them. And obviously when we look at this, we may want to consider metrics such as code coverage and such like, to ensure that the test bench has hit all of the paths through specific conditional paths and branches, or that all the flip-flops have been toggled and such like. Now that's really good, it gives us a good quality result, but what it can't tell us is always, it can't tell us what should be in the design that we've forgotten. But those metrics do give us some good idea as to what's going off in terms of the test bench and the design that currently exists. So just quickly looking at this slide, you can see that if they have 2 numbers A and B, say they're being added together, there are 4 corner cases in there when they're each at their extremes, to ensure that there are no wrapover or lockups, and then the boundary conditions are exploring the conditions around it. Now some people as well want to use constrained random vectors when they do this testing to further stress the design, and that's also very good, and there are a number of libraries and structures around, such as UUVVM and OVM, etc., to actually do this. So let's take a little bit of a look at a specific implementation now. And this is obviously based on my experience, it's based around particularly the Xilinx FPGA tool flow. So we're going to talk a little bit about the Xilinx slides now. So obviously the Xilinx development environment, Vivado 15.2, is certified for T2 and T3 tools. The GNU toolchain is actually certified up to SIL 4 or ISIL level D. And obviously there were other things that I've not mentioned in this talk as well too much, because there was a Xilinx talk the day after and I didn't want to sort of cover the same ground. But you know, within the processor system, we have the ARM trust zone, which allows us to create orthogonal worlds within software, such that we can have different levels of software running and they can see different elements of the hardware, such that we can have a much more safe and controlled and secure system. We have watchdogs within the processing system if we're using a Zynq, to ensure that if we lock up, we can come back okay. We have the XADC and Sysmons, as I mentioned earlier. Now what's really interesting is you think back to the global TMR and such like, and I was talking about how we would do the floor planning then there are tools that Xilinx make available, such as the isolation flow, which is available for both Vivado and for ISE. And there's also a verification tool that allows us to verify that we've implemented that correctly. Now, when it comes to configuration bits, sometimes there's concern over configuration bits being flipped and corrected. So we can use the essential bits technology and combine that with the single event mitigation IP core, which will look at it. And then if we're using the UltraSoC Zynq, which is a really great device, and there's even been devices added in there. So there's R5 real-time processors that are capable of adding in lockstep, and the actual device itself has really been considered to create IEC 61508 and 26262 designs to really simplify that further. So let's take a look at the isolation flow now. You can see that there's an example here where it's created two safety functions. It's put a logic fence around those to keep them isolated not only from each other but from the non-safety function on there, and that meets the IEC standard. If you look in the table, that says structures that isolate and decouple physical locations. So they're isolated there and they're decoupled from each other. So, and to run this, if we run this, I will do some tutorials on this actually in my blogs over the next few weeks. But if we run this, there's also a verification viewer that verifies that this isolation is being implemented properly. What this looks like when we put it in the final system is, you can see there the two isolated functions, the controller, exactly as we've got the block diagram on the left. You see the floor plan on the right, and you can see the implementation of it. So you can see where the functions are, and you can see the fences isolating them from each other as well. Now, this is also possible to use the Zynq to create a SIL-free HFT system. There's a really great Xilinx application note on how you can do this. And how they've done this is because of the system design and the design that went into the Zynq, they've separated the processor system from the programmable logic system, such that they are independent power supplies, clocks, etc. So there's no real common cause failures, and that allows you to use the Zynq processor cores with trust zone to implement one channel of the safety function, and put a microblaze in the processing logic, in the programmable logic even, to implement the second processing function and second safety chain. And now in this example, they can inject faults into both channels to actually make sure they're getting the safe failure fraction as they expected. And this gives you a real good example of how you can create a SIL-free solution in a single chip with a HFT of one. So when we talk about these systems, you may think that necessarily the complexity of them grows, the complexity of the solution grows, but actually that's not necessarily the case. Our jobs as engineers is to create the most optimum, elegant solution that meets the applications and the requirements possible. So when they applied so this is a quick example of what it looks like when you apply the SIL-free HFT Zynq example with the isolation flow, and you can see the microblaze over on the right, the trust zone over on the left. Obviously they're fixed in the silicon because they're in the PS and the PL, but you can see the temperature sensors being implemented, and the red lines implement fences in between each element. So you can see there the segmentation and isolation and decoupling between those functions. So really that brings me to the end of it now, and I'm going to wrap up and say, we really need to, my key messages are, we really need to consider the entirety of the system. It's not just the FPGA. We need a holistic approach. We need to consider everything all the way down, and we need to consider that both the safety, the testability, and the security of it all from day one. There are several FPGA techniques that can be used to achieve this, and there's some examples in this slide pack to do. And obviously an interesting message is that it's possible to implement a SIL-free HFT solution using a Zynq, which is to me is really exciting. So with that, this is the point where I asked for people to give me any questions in the audience. We had quite a few questions and some good discussion. It was a very well received talk. So if anybody has any questions, there's my website there. Please feel free to ping me an email or a message, and I'll try and answer them. But other than that, thank you for listening.